Attendees are in listen-only mode.
Okay, hi, welcome back again. So good afternoon, good morning, good night for all the people joining this webinar today. This is the first of the series of SAMOSAFER webinars. And this webinar is focused on an overview on the experimental facilities within the SAMOSAFER partners for thermal hydraulics. We have a very nice and wide set of panelists. So I'm going to move directly to the first contribution for today that is going to be given by Julien Giraud from CNRS. And so the floor is yours.
Okay, so hello everybody. Today I will present you the SWAT experiments platform at the LPSC Global, and I am Julien Giraud. Okay. So our lab is located in France, in the Alps here. In our lab, we have a dedicated building on for the experiment of molten salt and some other things like lithium. Basically, in our building, we have a glove box line. We also have our first molten salt loops called FFER, operating with FlyNac, starting in 2009. It's a forced convection loops. So today we will focus on the SWAT experiment platform. This platform started in 2015 with the SAMOSAFER contract, and now we are operating with the SAMOSAFER contract. So just to focus on our glove box line, it's very important because when we operating molten salt like FlyNac, we have to care about contact with oxygen or moisture. So this glove box is under argon gas. We use this glove box to produce the FlyNac that we will use in our experiments. For example, in each experiment, we use about 60 liters of FlyNac. So it's give a total mass of 120 kilograms of FlyNac in each experiment. So we have three glove boxes. The first one is used to mix the elementary powder that we use in the FlyNac. The FlyNac is made of lithium fluoride, sodium fluoride, and potassium fluoride. So we mix the elementary powder here. Then we transfer the powder in the second glove box, and this glove box is particular because we have a furnace directly connected to this glove box, and then we can add the powder and make like a cylinder of clean FlyNac. At the weight of this cylinder is about 6 kilos. And then we store all our FlyNac in the last glove box. We also carry out some experiments in this glove box, like experiment in solidification. So now, what's mean SWAT? SWAT means Salt at Work Thermal Exchange. So SWAT activity include both experiment and numerical developments. For example, with numerical development, we want to explore, for example, phase change, heat radiation, and then we use this numerical development to dimension, to design all the section, all the experiments that we will use in SWAT. So we work together, and we have a lot of meetings between the experimental part and the development part. And in order to converge with nice section and nice experiment, in order to have good data in terms of temperature, in data that will be an input or verification for the numerical development. So what's it SWAT? The experiment working principle. So what's SWAT runs with a FlyNac. It has a discontinuous working. We don't have pump on SWAT. The SWAT flow is initiated, in fact, by the pressure difference in the tank. The upstream, for example, we increase the pressure in the upstream tank, and then the fly nac go into this pipe throughout the glove box where there is a specific section and go in the downstream tank. So we have two different components in SWAT facility. We have the facility itself with the pipe and the tank, and we have the experiment section, which here are located in the glove box. So, of course, we don't have a continuous flow. We have a limited quantity of salt of about 60 liters. So, depending on the flow rate, we have some variation of duration of our experiment between 2 hours for the longest and for the smallest about half an hour. So why we use fly nac in SWAT? Fly nac is when we focus on heat convection transfer and based on the print number, we can see that fly nac is a good candidate if we want to simulate lithium fluoride, thorium fluoride for normal and accident temperature. So here we have lithium fluoride, thorium, and here we have the fly nac. And for normal operation and accident operation, we can see we can work for a range of temperature between 500 to 700 degrees, and we have good representativity. So, but before starting to build our, our stainless steel experiment for the fly nac, we always start to design and operate that we call SWAT-W, SWAT water. In fact, we build a replica, a copy of SWAT, and then we operate this copy with water, compressed air, and we made all this experiment with transparent plastic. Then we can have experimental measure with when we can control pressure, we can check the flow rate into our experiment, and then we can also have result with when we use PIV method to see if our prediction with the simulation is in good adequation with our flow that we can see with PIV. So when we decide to use this plastic experiment, in fact, it's very, very important because we reduce the risk for the development. Because when you build an experiment with stainless steel, it's hard to have change. But when you start to build an experiment with plastic, you can evaluate your design, we can iterate, and then find the nice configuration. So let's look SWAT-W platform. It's exactly the same as real SWAT S for the salt. We have two tanks, the upper tank here and the down tank here. We control the flow by air injection. All the small pipe in yellow is the distribution of the air pressurized. We use, of course, some pressure sensor. We have here flow meter. And then basically we start to pressurize this tank. So the fluid go into this pipe and go to the flow meter and go into the experimental section and then return to the downstream tank. So we use this experiment to develop the control. And then, of course, we work a lot on the experimental section. So here you have an example of hydraulic experiment. For example, the back step. Here you have the inlet of the back step. Here you have the outlet. The length is about 1 meter. The thickness is about 30 meters. And we use we perform PIV on this section. We develop the flow control in order to have very stable control of the flow in this section, and we compare the result of the PIV with Hans model and other simulation. So, for example, here you have results for the PIV method. So PIV works with laser illumination of the flow and camera who films this section, and we can reconstruct after on post-treatment all the speed in the fluid, and we can of course have a error. And then we compare this result to different simulation, RANS model, LOS model, and then we can compare the simulation and the experiment. So now let's go back to the SWOT design. So we use salt is FlyNac, the total volume is 50 to 60 liter. The operating ground temperature is about 500 to 700. So, and if we compare the flow rate and the times that we can have access to the data, it's about maybe 10 minutes to 2 hours. But generally, we prefer to have a long experiment, long time of experiment, in order to have a steady state temperature into our experiments. So generally, we use SWOT at about 0.5 liter per minute. So it gives 2 hours of experiment. So now you have a picture of the SWOT in his dedicated room. When I mean dedicated room, it's, for example, in such installation, we'd always have a flow of air in circulation to evacuate all the receipts of gas or something like that of insulation. We can find the first tank, the upstream tank. We have the glove box right here. We have the downstream tank. So how does it work? We start to pressurize this tank. The flow initiates in this pipe, go into the glove box and in the section, go to the glove box and return is downstream tank. And after we close this big valve, we pressurize this tank and the salt return in the upstream tank by this pipe. So of course, on this installation, there is a lot of gas distribution. All these small pipe in yellow or in green, we have a lot of valve. Mainly is for distributing argon, because we always have a cover gas that is argon in when we are in operation and where we are at room temperature for storage of the FlyNac. So now let's focus of the flow rate measurement, which is crucial when we start to work with molten salt. In fact, there is no commercial development for the salt, especially for FlyNac at this temperature. So we decide on the SWOT to have 2 tanks. On each tank, we have proportional measurements of the level of the salt in any time. So it gives us a proportional measure of the tanks, and we can easily calculate the flow rate. And we have a discontinuous, so it gives us an average of the development of the level of the salt into this tank. Of course, we have a post-treatment of this indication with an electronic, and then we can have access to the flow calculation. So if I sum up, we have 2 tanks, and on each tank we have 2 measures of the flow rate. So in total, we have 4 measures of the flow rate in the section, so anytime. So we can have a good appreciation of the flow rate in our section. That is good news when we look at the thermal effect. So now just focus on flat channel development. So generally in SWOT we have the pipes, the diameter of the inner pipe is 20 millimeter. We decide to, for some reason, to switch in our section to have a rectangular channel. The thickness is 5 millimeter and the width is 150 millimeter. So we make this channel in plastic in SWOT W version. We make some PIV on this flat channel that we can see the flat channel right here. And for example, typical image, what we are looking for on this development, we want a good transition between our round pipe and transitions the round pipe to rectangular section. So we iterate and find a good shape of our diffuser. Here you can see a picture without diffuser, and here you can see a picture with a developed diffuser that give us good results. So after that, after we validate our design in SWAT-W, we built our section. Here we can see the flash section in stainless steel. In fact, we use 3 or 4. But basically, in stainless steel, we can see have access to the form of the fluid into this section. So that's why we do some PIV method on plastic section. So what is noticeable in this kind of experiment, we have access to thermocouple, temperature by the thermocouple. That's the only things that we have in this experiment. So we are very careful or where we locate the thermocouple and where we locate the heater. On this experiment and all experiment, we always have some heater. It's a strip. We have strip heater here or some round heater here. It's just another for preheat all the system at 600 degrees before starting the experiment. But in this experiment, we have to build specifically this main heater. So give us about 3 kilowatts of power. So we heat on this side, and then we measure on the other side, and we have about 15 thermocouple on the measurement side, and that will be our input for the comparison between simulation and experiment. So, but because we are at high temperature, of course, if we want to reach the temperature to 600 degrees generally, but specifically on this section where we need the 700 degrees on this face, we have to insulate a lot our experiment. Generally, we need to about 20 millimeter of insulation. So we start with our insulation is like foam, in fact. And then when we finish, we cover with aluminum in order to reduce the heat loss by radiation. So we are here, I'm finishing the insulation. And just to see the control room, in fact, here we have the global control room. What we are piloting in SWAT, mainly we piloted with all this box is a PID which controls the temperature of the preheat system. All the pipe are preheat, all the pipe, all the valve of all the tanks are preheat at about 600 degrees. Here we have the electronic for level measurements. Here you have the electronic for the temperature into the section. We can control temperature, but we also control the power that we can input into our section. So for controlling, we need some development in LabVIEW. We can see here, this screen is dedicated to measure some temperature. So some have some controls argon cover gas regulation. And this screen is dedicated to the flow control. We have to iterate a lot to find the parameter in order to have a continuous flow into the sections, and it's working with LabVIEW. We have another screen here. We only have data logging. We use smart data logging right here, and here we have a manual control panel in case of emergency. And here we have a typical view of our data logging. In fact, where we talk about data logging, we data logging the pressure. We data logging here. It's the level into the tank directly from the laser. We have directly the measurement in millimeter. And of course, right here, it's during operation. We have a lot, about 70 thermocouple in all our experiments, and 40 thermocouple, it's represented here, into our section. Okay, so thank you for this presentation, and if you have some question.
Thank you, Julien, for your presentation. I just wanted just to specify that according to the scheduling of this webinar, we decided to have the presentation of the different panelists, one after the other, and then we'll reserve some time at the end for entertaining the questions. So this means that I'm now asking my colleague from Politecnico di Milano, Stefano Lorenzi, and that I have to make presenter, to continue with the presentation regarding the facilities in Politecnico di Milano.
Thank you, Sandra. So let me see if it's working or not. Are you seeing the full screen presentation or not?
Not full.
Not full screen.
Yes.
Okay, now it is.
Okay.
Okay.
Thank you very much. So in this presentation, I will provide you, let's say, an overview of the Dynasty experiment that we perform in Politecnico di Milano. So I've just still a slide from Professor Ribero's presentation. Sorry, Pablo, for that, but I found this presentation very useful to introduce our topic. So you can see that the question why performing thermohydraulic studies, the answer is to verify the reactor design and safety requirement. But you can see that there are several processes in that. In our case, in our specific case for our, let's say, experimental effort, what we want to do is try to, let's say, comply with the requirement of passive safety system. You are aware of the fact that we had a Fukushima accident that pointed out the importance of having a system that can, let's say, comply with the safety function regardless the activation of component, the active, let's say, initiation of the component. That's why we want that also for the generation 4 reactor, we want to have some passive system for improving the reliability. The fact is that for SM molten salt fast reactors, or in general for circulating fuel reactor, we have this peculiar feature that the heat is directly released in the fuel coolant. So if we come back to this arrow, so which is the impact on design and safety criteria of this requirement. So we should ask ourselves how the passive safety system behaves in natural circulation with this uncommon feature. So how can we design the passive safety system with this feature? Once again, if you remember the slide of Professor Rubiolo, in between the requirement and the design, we have the phenomenon. So the very first step to tackle this problem is try to understand which is the basic phenomenon under that, let's say, govern this on the one hand the requirement, on the other hand our system. And in our case, if we speak about decay heat removal in presence of internal heat generation, we have to look at the natural circulation. So when we speak about decay heat removal system with passive, let's say, features, we want to, let's say, promote a fluid flow with the natural circulation. For sure, I mean, natural circulation is quite, let's say, complex phenomenon, because it involves on one side the buoyancy forces, so the lift due to the density to the density gradient inside the fluid, and on the other end, it involves the pressure losses that the fluid encounters in its path. So basically, it's really the balance between these two, let's say, forces that, let's say, promote the fluid flow. But on the other end, the fluid flow, so the results of these forces as an influence on both the pressure losses and the temperature. So you can see that there is a strong, let's say, connection between all the elements that makes the natural circulation quite, let's say, a very nonlinear phenomenon. And classically, I mean, in the field of nuclear, let's say, nuclear reactor, natural circulation system can experience some problem related to the instability. We can see, and we have seen in the past, different, let's say, instability events, mainly related to the boiling water reactor, but still boiling water reactor and, let's say, natural circulation feature. Here I reported just two events that, let's say, trigger an instability event, both in Caorso and in La Salle nuclear reactor. And from the picture, you can see that when we talk about instability, we have to discriminate on one end, let's say, the mathematical concept of the instability. So you have a sharp increase of some quantity, and on the other end, the physical one. So the physical one means that you have this, let's say, continuous oscillation of your variables. In this case, the power or the core flow or the steam flow in this case. So, and for sure, this is a condition that we want to avoid, because there is a continuous stress on the component, and on the other end, we have let's say, the value of our variable are not can be not in a safe bandwidth. But we told about boiling water reactors, so mainly here, the instability is due to the two-phase, let's say, phenomenon. But here, since we are talking about molten salt reactor, here we have a single phase. So in single phase, let's say, the main let's say, natural circulation single phase system, the main problem is related to the density wave instability. So this it's an instability that it's really linked to the dynamics of the system. So a density wave is nothing more than a perturbation in density of the fluid mixture that travels along an ether channel. So you may think about to have a natural circulation loop in which you have the ether, which is the portion of the loop that provide power, and then a cooler, which is a section of your circuit that extract the power. And you may think that, okay, you have a not packet, let's say, here in the ether zone. So this hot wave packet start to, let's say, go along the riser, and since it's hot, this promote natural circulation, so promote the buoyancy forces, then promote the an increase of mass flow rate. But if I have an increase of mass flow rate, this means that my, let's say, temperature, which goes, let's say, across the cooler, it's reduced with respect to the previous situation in which I have a lower mass flow rate. And then since I have a lower mass flow rate, a lower temperature, then a colder, let's say, wave packet start to travel in the downcomer and through the ether. But then inside the ether, this wave start to, let's say, increase the temperature and so on and so forth. So you see that you have this balance between the heating part and the cooler part, and the fact that you have a fluid which is traveling along the along the loop. So I can show you here a picture of a possible, let's say, natural circulation loop. You can see that it's not just a matter of oscillation, but you can end up with a reverse flow, which is the worst condition that you can have in a circuit, and especially in a circuit which is dedicated to the heat extraction, like a dedicated heat removal system. And if you start back, so you have the heater, it's actually located alongside all the circuits, so both in the two vertical part and the horizontal part. And here you have the cooler. So the fluid start moving in a clockwise direction, but then suddenly you see here a cold vein that is producing the cooler that basically push down your fluid, and you have the reverse flow. So the process that guides this phenomenon is really related to the let's say to the physical parameter of the loop and the physical parameter of the fluid. Usually this kind of problem has been let's say considered just for a localized heater and the localized cooler, but then if you have a molten salt, which you have a internal heat generation, you basically have a different problem. You have to solve a different problem, because what guides the mass flow inside the fluid are, once again, the delta T and then the density gradient alongside the loop. If you are changing the power imposed alongside the loop, then you have a different, let's say, configuration. So once again, we want to study this problem from the very beginning. We want to focus as first step on the phenomena. So we need something that it's quite easy to build and to study. And this is why we decide to build in our department a natural circulation loop that has the feature of having a distributed heating. And when we decide to go in this direction in order to study the problem, we ask ourselves, okay, which is the process that I have to follow in order to, let's say, prepare the experiment, design the experiment, prepare the experiment, and getting some result from the experiment, some useful result of the experiment. So as a first step, we develop some analytical and numerical modeling to, let's say, to build and construct the dynasty in order to have, let's say, the grasp of the feature of the experiment that we want to perform. Because, for example, I mean, we can build our natural circulation loop in condition that it's always stable, which is not good, because we want also to understand and to study the unstable condition of the facility. Then when we had developed this analytical and numerical modeling and construct the dynasty, then we want to perform some experimental campaign, which on the other side will be useful to validate the models that would be useful for studying the phenomenon. Actually, I will not too much in detail about the modeling, but the different phases of the experiment have required different modeling approaches. For example, for the stability map, that provide a very, let's say, engineering information about which point is stable or unstable. Each point can be characterized by a thermodynamic condition, in this case, a Prandtl and a Reynolds number, or some conditions that are more, let's say, typical of the facility, which could be the temperature of the cooler or the power imposed to the facility. And this kind of modeling has been useful during the preliminary design. Then we moved to a 1D model, which was used for some design optimization for transient behavior. And then let's say the other modeling option that we can have is the 3D CFD model, which, I mean, the importance of the CFD has been already mentioned by Professor Rubioli. So at the end of the day, we built Dynasty in order to study this phenomenon. The facility can work with the three main fluid: water plus glycol, and molten salt. The use of water plus glycol was driven by the fact that this, let's say, mixture can be used to study through the thermal hydraulic similitude the molten salt. So we can try to extract some useful information from the water, from this mixture. And you can see here so let me just switch to the laser point, the facility. So you have this is really a natural circulation loop in which you have two horizontal leg, the one for the forced convection, here you have the pump, and then the one for the natural circulation experiment. When we want to perform a natural circulation experiment, we just basically close this leg, and the path will be this one. The heated section are three. The first vertical leg, the second vertical leg, and the horizontal. And then on the top of the facility, we have the cooler, which is a finned pipe with a fan that extract the heat from this section. So here you can find some characteristic. For example, the heating system is made with some stripes that are alongside the pipes. This let's say choice has been guided by the fact that in our analytical model, it turns out that for a 1D system, and basically a natural circulation loop has mainly a 1D characteristic, the internal heat generation can be basically studied through a distributed heat generation, because the 3D, let's say, characteristic, it's not so, let's say, it doesn't determine a variation of the property of the system. We have also actually another facility, which is called eDynasty, which is another loop which is coupled through an heat exchanger. And this has been built in order to study the coupled behavior of two natural circulation loops. So in the Dynasty will be the distributed heating, here will be a localized heating. As for the instrumentation setup, the facility is provided with 4 fluid thermocouple located here, and here. This thermocouple provides us the temperature information in the fluid in 4 points of the system. Then we have up to 8 wall thermocouple in order to record the temperature of the wall along the experiment. In addition to that, we have a mass flow meter that helps us in the recording of the mass flow rate in case of natural circulation experiment. And okay, then we have also the fan. We can control both the fan power, which will control the temperature inside the cooler, which is one of the main, let's say, governing parameter of the facility. The other one is the heater. So both these two, let's say, knob. These are the two knobs that we can use for varying the condition of the operating condition of the facility. So I want just to share with you the result of the water experimental campaign, which has been conducted in order to assess the influence of the fan velocity in different cases. So we are working with water and no insulation in order to evaluate the thermal losses. And then we have a 4 heating configuration. So the vertical heating and the horizontal cooling with the first vertical leg, vertical heating and horizontal cooling for the second vertical leg, the horizontal heating and horizontal cooling, and the distributed heating. Basically, this is the experimental matrix that we performed for this campaign, and as you can see that we can vary this is the fan velocity that basically varies the temperature inside the cooler section, and here you can see the different configuration. So about the result, the most important result that we can obtain, it's on one hand the mass flow rate inside the facility. So we turned on the vertical heating, and then slowly, this kind of experiment takes let's say a considerable amount of time. Here we can see that it's 25,000 seconds. So we turn on the heating system in the vertical leg, and then we can start to see movement of the fluid inside the facility without obviously any pump inside. And these, you can see the differences here with having no the fan at 0% and the fan at 75%. The difference is not only on the, let's say, up to 15,000, it's the, let's say, heating phase. After that, we just shut down the power and we let the facility cool down. You can see that not only in the heating part, but also in the cooling down part, we have, let's say, a different behavior of the system. So going back to the heating part, here you can see that we can see quite an higher, let's say, value of the mass flow rate if we mostly remove the heat from the cooler, because when I talk about fan at 0%, this means that if we don't have insulation, the heat is also dissipated through the tube through the different part of the facility. And these are the temperature profile. This is here you can clearly see that some part of the facility are acting as a heater, GB1, but if you don't have the insulation, you will have not only this part as cooler, but also the GB2 and GO1 that acts also as cooler. We perform also the experiment with the horizontal heating, which in principle from both theory and from the analytics model should be the most, let's say, problematic from a stability point of view, because you see that the system is becoming very symmetric, and so then the water, let's say, it's more prone to, let's say, to instability. And actually what we saw is that, especially from the very first part, we have some, let's say, remarkable oscillation in the mass flow rate. This experiment also helps us in confirming that this kind of phenomenon, it's governed by let's say, the movement of this hot and cold wave packet. Especially, it's clear from the very beginning when we have this oscillatory behavior, in which really you see that the peak are transferred from one point to another. So this experiment was very useful to confirm this theoretical background that we developed. And for the distributed heating, here we are getting the hottest temperature in the facility, and once again, I mean, also this kind of configuration, it's quite, let's say, symmetric. So we are expecting to have, let's say, the most, let's say, problematic one. And here you can see that we have some oscillation and some spike even if we are not, let's say, introducing any perturbation in the system. So, and once again, here you can see also the temperature profile. So I have almost run out all my time, but I mean the Dynasty facility will be used also in the SAMOSAFER project to continue the experimental investigation. Especially, we are planning also to have an experimental campaign using the water plus the glycol fluid in order to, let's say, verify the similitude between the ITEC and the so the molten salt ITEC and the this glycol. Then, if let's say the technology assists us, I will stop sharing, and then I will ask Carolina to guide you in in a virtual tour of the facility.
Yes. Can you see something?
Yes, perfectly. We can also hear you very well.
Nice. Okay, cool. Okay, so sorry for the background noise, but okay, that's unavoidable. So let's start with the data acquisition software. I don't know if you can see it. Okay, maybe. Yes, kind of. Anyway, okay, the data acquisition software is based, as you can see here, or maybe not, but trust me on this, on MATLAB, based on two different boards, which are enclosed for safety reasons in their boxes. So with this system, we can control the power that we give to the stripes, so to the three legs, in order to perform various kind of experiments, and also, for example, to study what happens if you wait a moment. For example, here, what happens following a step increase in power. And again, here you see, as we said before, the very nice wave packets for the heating transit. Okay, so now we go to watch Dynasty. Okay, as you can see here. So here we are seeing the horizontal leg, so G01 with the stripes, the mass flow meter there, and the pump for studying cases of forced convection. One thing, in the future we will put the insulation to the facility. But I mean, this is actually advantage that you can see how the facility is without the insulation. So that one is one of the 4 thermocouples installed for the fluid. This is the one is TC4. So as you can see, is like the point of the thermocouple is in the middle of the channel. So now let's wait a minute so that we go. Okay. Okay, be patient that I'm going up. I'll try not to kill myself in the meantime. Okay, so here we are seeing this is GV2 with its stripe, and here we have GV1. Okay, like let's go there. Okay, here a nice view of our very beautiful study in Dynasty. Okay, a moment that I'm going back down. Okay, I won't go to the upper level because I think it's too dangerous. Okay. Okay. Then, other than Dynasty, you can see here we have here this is E-Dynasty, so the coupled loop that we give a yes, this is a nicer view of the lower part of Dynasty with E Dynasty. Okay. Oh yeah, here I don't know if you can see because it's quite dark, but I'm pointing to the fan system. So it's yes, it's very dark. Unfortunately, we don't have a light source here. Yeah, maybe here it's okay. Okay, here's still a view of here. Yes. Okay, this is the whole of the GV1 length, which is nearly 4 meters long. So you can see it's, I mean, it's bigger than what it looks in the slides. Okay, so I think if Stefano agrees, that's all for me. I mean, we cannot go to the topmost level because going to the ladder with one and on is quite, I mean, a bit dangerous, so I will skip that. But you can maybe see there the loading tank. Maybe, yes, on the right. And here we have the discharge tank. That's along with the E Dynasty tank. Okay, so I think that's all, right?
Yes, thank you, Carolina. Thank you very much.
You're welcome.
I hope enjoy this, I mean, virtual tour of the facility. Yes. So we are more or less in line with the program. So now I will give the floor to Dr. Marek Stempniewicz. I hope that I pronounce it correctly. Which is from Energy, that will talk about Msri experiment and the simulation tool Spectra, which is developed in Energy. So I will give you all the right to present, Marek. Okay.
Okay, thank you. So I hope you should be able to see my screen now.
Yes, it's not in a full screen mode. Perfect.
Okay. Okay, great. Okay, great, thanks. So I just want to say a few words about the simulations of Msri experiments with Dynasty using the spectra code. So I will say first just a few words about spectra very shortly, and then I go right to the main topic, which is I have here the two main topics. One is the delayed neutron precursor simulation, and the other one is the simulation of the fission product behavior. So first, I will give you a very short about spectra, very short information. It's a system code, and then I will say a few words about those subjects that I mentioned. So the delayed neutron precursors and the fission product behavior, including noble gases and noble metals. So for the spectra code, it's a system thermohydraulic code, which is similar to Melcore or RELAP 5, and it's applicable for different reactor types, and among others is molten salt reactors. We are using it as a standalone system analysis tool, and also coupled to CFD and 3D kinetics. So the spectra is like in Melcore and RELAP, it has point kinetics model, but we couple it to 3D kinetics and also to CFD 3D simulation tools. So we are using it for design support analysis and also for the safety analysis of molten salt reactors, the new designs of molten salt reactors. So that there's one design which we have at NRG. We're designing an experimental MSR look, which was in 2015, and through 18, and another one which is happening right now, and then there is also another MSR design we are busy with right now. So first of all, I'd like to say a few words about the first subject. Is about tracking the delayed neutron precursors in molten salt reactors. So first I want to say a few words. What is the delayed neutron precursors? I'm sure that everyone knows it perfectly well, but I would like to mention it very shortly. So these are just a special type of diffusion products that those fission products which emit neutrons when they decay. So you have the fission products being created due to fission of uranium or plutonium, and then the fission products with certain half-life, they decay and they produce neutron, which is called then a delayed neutron because it's generated with some delay compared to the fission process. So we have here, I put some table with the typical delayed neutron precursors. So you can see those fission products here. There are different fission products, and they characterized by different half-lives. So you have the half-life which is between 0.23 seconds and 56 seconds for uranium, here for uranium-235. And also you have the total fractions, which is for uranium-235 is 0.6% about, and it's much smaller for the other ones. Okay, so first I would like to say a few words about the point kinetics equations in the standard situation. So when we have the normal reactor, let's say we have a normal, not like a molten salt where everything is flowing around. So we have those equations, which I think everyone knows pretty well. So those concentrations of the delayed neutron precursors are governed by the production from fission, and the removal is due to radioactive decay, and this removal from radioactive decay is producing neutrons, so this neutron production is included here. So this is what's happening in a normal, let's say, LWR reactor. Now, what happens when we go to molten salt? What happens with this delayed neutron precursor? So the fuel is dissolved in the salt, of course, and it's flowing around together with all the fission products. So consequently, the fission products, including our delayed neutron precursors, are circulating with the salt. And so as a consequence, we have less delayed neutron precursors in the core. So effectively, we'll have less than those numbers which I was showing here. So this is 0.64, 0.21, 0.26. This is the fraction of delayed neutron precursors that are normally in the core generated. And now in the molten salt, it will be less than that. So this is what we don't like, because as probably you all know, the delayed neutron precursor make it much easier to control the nuclear reactors. So we don't like the fact that we lose some of them, but we cannot help it very much. Okay, so before we can enter into very complicated mathematical description of what happens with the delayed neutron precursors in the circulating fluid, I'd like to explain this thing in a very simple way, because it's late afternoon, so let's just take it easy and let's think about it. What happens when you stop the primary pump and we have no movement of the salt? So we get back to the standard point kinetics equations as we've seen them here. So all of that, what is generated, is staying in the reactor core, and it's decaying there, and it's providing the neutrons to sustain the fission reaction. Okay. So now what happens? So here I say, here, this I wrote the balance of the delayed neutron precursor. We have the source, we have the radioactive removal due to radioactive decay. So the source is given here. And now what we normally do is we make a model of the reactor core. We discretize it into a certain finite number of nodes. So this total source of delayed neutrons, we have to sum up this, all of the nodes that are belonging to the core. So you can see here, let's say, if we have certain distribution of flux in the core, what we have is we will have also certain distribution of the source. So we can say, okay, the distribution of this source will be proportional to the distribution of the neutron flux in the core. And in our situation, the delayed neutron precursor distribution will be proportional to the neutron flux distribution. So we can determine the space dependency of the delayed neutron precursor in the core as a function of location. And now what happens when we start up the pump and let it flow? So what we have so far is we can use so far before we start up the pump, we can use the same equations. Now, when we start up the pump, what I'm saying now, it's just one of the possible approaches. I've seen a couple of days ago the model they use in Melcore, and it's quite different approach, but it's also a good approach, and it's a standalone sort of package. But here in this case, we decided that we couple the kinetics equation into particle tracking model. So the idea is that we assume that the delayed neutron precursors are just like with any other fission products. We link them to the particle tracking model in the code, so they move with the same velocity as the fluid velocity. So once we start up the pump, what we have is we have the movement of the fluid, and we have consequently the movement of the delayed neutron precursor. So if we start observing what happens with this delayed neutron precursor, you will see that the distribution will be shifted. I don't know if you can see this. Okay. So the distribution will be shifted upwards along with the flow. So what we do now with the point kinetics equations, we sum up the concentration which belongs to the core. So only the nodes that belong to the core region, we're summing up, because now the delayed neutron precursor are all over the primary system. So we sum up only those which are in the core region, and we use that contribution in the point kinetics equations, which you see here. So the decay of the delayed neutron precursor, which occurs in the core, is taken into account in the point kinetics equations. So what we have is we have the delayed neutron precursors decaying in the core, which is less than, obviously less than the total amount, and therefore our nuclear reaction will need external reactivity. Once we start up the pump, we need external reactivity to continue the reaction. And this process described above, we used, there was experiments done on Msri Reactor, and we analyzed that, and I will mention that in a moment. So Msri Reactor, I think that the community knows very well, because then everyone is, well, it's quite well-known reactor, so I'll not go into details. That's the Oak Ridge National Laboratory Reactor, and they were using uranium-235 and uranium-233 as fuel. There was primary salt and secondary salt, and we made a model of the Msri for the spectra code, and we describe it, and I mentioned here reports and publications where this can be found. So I just go through it. Also, this is the core model what we have, and also this is showing the steady state parameters. So we compared the thermohydraulic results to the source data, make sure that we get reasonable agreement, and those are published as well. It's mentioned in the list of publications. Now we move to first thing what we did is we checked the distribution of the delayed neutron precursors in the core against the Oak Ridge model. So this figure here is showing you the delayed. So first, this one is basically the source distribution, so or the stationary state situation, and this is the red dots are just generating the representing the values calculated for the non-flow situation, and the blue dots for the flow situation, and then they are in good agreement with the model that is that was used at Oak Ridge. So those were the steady state. So this is the steady state situation. It's just you see that the delayed neutron concentration when you have the flow is shifted towards the upper part of the core. So now I would like to show a couple of things about this zero power pump startup and pump shutdown test. They were performed at a very low power. So what we have is in this situation we have we starting up the pump. And then when we start up the pump, this what happens is that we lose some of the delayed neutron precursors, and therefore we need extra reactivity to maintain the reaction at this desired level. So there is some control system which moves the control rod up to keep the desired power. And we did that calculation and compared it with the experimental results, and there is a description of this in those references which I show here. So basically, this one is showing this graph is showing the reactivity that is needed to keep the desired power. So what happens is we have to insert reactivity because after start up the pump we have we lose delayed neutron precursors. So you can see that it's well in good agreement qualitatively, but the height is, the insertion of reactivity is calculated is a little bit higher. So what we were thinking, what could be the reason for this overestimation? So as you remember, in this case, in our model, we sum up the delayed neutron precursor contribution from the core section, so from all the nodes that are belonging to the core. And then we figured, okay, what happens with, in the upper plenum, just above the core? You still have plenty of salt there because the graphite is stopped and there's no graphite in the upper plenum, so you have the upper plenum is full of salt, and then there is also a lot of those delayed neutron precursor flowing there, and some of them are decaying in the upper plenum, and specifically part of this can be affecting the reactivity. So we did is we took this concentration of the delayed neutron precursor in the upper plenum, and we took 1/6 of those because the rationale is that if you on the average 1/6 of the emitted neutrons will be emitted towards the core. So we added this term into this term, which is normally added. So the sum of the delayed neutron precursor in the core region. And then when we did that, we got actually very close match to the measured data. So that's one thing, and we're publishing these results together with our colleagues from Argonne National Laboratory who do the same simulation using their code, SAM, and we will be publishing those together. So another similar is a shutdown test. So we have now the normal operation. We shut down the reactors. So this is the pump curve, and then this is again the reactivity effect. So in this case, we shut down the reactor, we shut down the pump, so we have no flow, and therefore we have to remove reactivity from the core because it's the other way around as before. And again, we have the same situation as before. We have somewhat overestimated the effect with the default model, but when we accounted for the 1/6 of the upper plenum concentrations of delayed neutron precursor, then we get a pretty good match. Okay, just a few words maybe about fission product behavior. So first of all, we have a large number of fission products, and we can divide them into 3 groups. So the first groups, which is called salt seekers, or those are the fission products that remain in the salt and they don't do much. They just flow around with the salt and stay there, and those are sort of neutral. And then we have noble gases and noble metals. So noble gases are, of course, those are the xenon and krypton, different isotopes of xenon and krypton. And those are easily transported to available gas, such as gas bubbles. In MSRE, they had this gas bubble or helium bubbler to remove fission products. They also easily move to the pores of the graphite, the moderator graphite, and they diffuse into the graphite, as I will show in a moment. And so there's a lot of those fission products may be found there. And then the last group is noble metals. The noble metals also migrate easily into graphite and also metallic structures, and they have been found in MSRE, they have been found in salt, in gas phase, and in metallic walls of crystalloid walls and graphite heat exchanger tubes. So they basically go everywhere, and they connected to everything. Just very shortly, we have this one example of the noble gas behavior. So we took, so again, there is a number of those analyses that have been published in the publications that are shown in the reference list. We just selected one of them, which is relatively nice case. So we have a short-lived isotope of xenon-140, which decays into cesium, and then this one decays into barium, and that barium is comparatively stable. So what happens is then, xenon is going into graphite easily and diffusing within it. And then it's decaying, and then the daughter products like cesium and barium can be found there at different depths. And so this is the experiment described in one of the Oak Ridge report, which I mentioned here. So then it takes the whole experiment, it took several months, it's 1,100 hours. And then there was a break during the reactor was operating for 2 periods with some break in the middle. So you can see that this is the concentration of barium-140. It's in graphite, it's increasing, and then was decreasing and then increasing again. So we did this whole simulation of the operation, and then you can see the results here. So basically, if you look at this graph, what I show here is this is the concentration of xenon isotope. So xenon is migrating into graphite and diffusing into it, and then it's decaying into cesium. Well, cesium is observed in more or less the same concentration because those are very short living isotopes, and then the cesium is decaying into barium, and barium is actually measured, and the measurements are given in the Oak Ridge report. So we did the simulation, and we plotted the concentration of barium versus the depth in graphite, and we have pretty good agreement with our calculations. So that's one thing that illustrates what happens with those fission products, the noble gases and their daughter products in the reactor. So a lot of those fission products can be found in graphite because of that tendency of migrating the xenon noble gases into graphite. And another one, what I have here is the fission product, the noble metals behavior. So just very shortly, noble metals, it's just a mess. They migrate to graphite, they stick to metallic structures, they stick to circulating gas bubbles. So it's making it very difficult to simulate. And they measured some global distribution of noble metals in different parts of the reactor, and it can be found in the reference that I mentioned here. And we did try to analyze some of the noble metals. So this is the example, one of the examples is tellurium-134 chain. And we compared our results with the observation of with measurements from Oak Ridge. So these are the results, and they were published in Nuclear Engineering and Design. So it's also, there is a reference to it if you want some more details. But you can see it's reasonably good agreement between the distribution, the measured distribution, and the calculated distribution. Okay, so I just want to summarize what I've shown you today was that I've shown the delayed neutron precursor model and some results, including stationary state and pump transient, so pump startup and shutdown transient. I've shown some examples of noble gases and noble metals fission products in Msri reactors, and those were selected to illustrate the phenomena that are occurring in molten salt reactors. So there is a circulation of fission products, and including delayed neutron precursors through the entire primary system, and those fission products tend to interact with graphite, with metallic surfaces, and with bubbles. Right, so yeah, the MSRE features that include helium bubblers. So they had this bubbler that is including helium to remove fission products, specifically noble metals and noble gases, and xenon stripper also. Those were also included in the analysis. So the xenon stripper is a thing like a ring with small holes which spray the salt. And by spraying the salt, you remove noble gases because you create small particles of salt with noble gases like xenon or krypton can be removed, and we take that into account in an analysis. Okay, so this is all I have for now, and then you have all the references which you can find more information